fact, within density functional theory, the famous Kohn-Sham formalism, which is the basis essentially of everything which these days is done in density functional theory. I should mention that not all density functional theory work is really in the Kohn-Sham framework. So if you remember last time, we have introduced these Kohn-Sham orbitals and the single particle orbitals for one particular reason, which was the kinetic energy. Okay? And I said, if one just uses their Thomas Fermi or some other approximation for a kinetic energy as a function of the density, then this does not give very good results. But some people are still working on this. So, and it has received recently, again, some popularity. The way of using density function theory really by only looking at the density without any Kohn-Sham orbital. So this is something which exists. And I just wanted to let you, to mention the name. This is called orbital-free density functional theory. So orbital-free, if you read somewhere OFDFT or orbital-free DFT, this is it. So there people use, they do not use Thomas Fermi, but they use some more sophisticated expression for the kinetic energy written only in terms of density and gradient of density and so on, so, but only as a function of the density, and then they get away without the Kohn-Sham formalism. But this is really, with respect to the number of people who work in DFT in the Kohn-Sham framework, this is perhaps 0.001% of the scientists who work in this. So it's really something, I mean, perhaps there will be a big breakthrough in the coming years, who knows, but today, when one says DFT, one means what we have seen, which is essentially the Kohn-Sham framework in DFT. Okay? And what we have seen in the Kohn-Sham framework was that we have, so we know that in DFT we have the total energy of our many electron system. Okay? We know that in principle it is a functional of n, of the density. Okay? So this is by Hohenberg-Kohn and so on. For our convenience, last time we introduced kind of a change of variables. Okay? So let me call this here E tilde, and we have introduced the energy as a function not of the density, but of the set of Kohn-Sham orbitals. Okay? And then I was insisting very much last time on the fact that we are not trying to do Hartree-Fock. So even though these are single particle orbitals, like they appear in Hartree-Fock, we are, as long as we are in DFT, we are not attempting to say our wave function is a determinant made out of them. Okay? So we are never talking in all this, we are never saying, making an expression which depends on one determinant there and some matrix elements of determinant. We are not doing this. This is a wave, would be a wave function theory, would be Hartree-Fock. So what we are doing is nothing like this. We have introduced these orbitals simply because we would like to write the density n of r as a sum over these variables. So it is phi I complex conjugate of r phi I. Okay? This is basically the, and you can see this if you want as a change of variables, mathematically speaking, where you say instead of taking the basic variable n, we take the phi's as basic variable, and they are such that, well, you have n of them, as many as you have electrons, and you want them to be orthonormal, meaning this here is delta. Okay? It is 1 if it's the same orbital, so it's normalized, and it is 0 for two different orbitals. Okay? So we have introduced those so-called Kohn-Sham single particle orbitals, and the reason we introduce them is that we get an expression for the kinetic energy, and that was minus the sum over all electrons, and here we simply h bar square over 2m, and then we have integral over all space phi I complex conjugate of r gradient square phi I. Okay, so that is the expression we have written for the kinetic energy. It looks like the kinetic energy you also find in Hartree-Fock, because also there you have simply the sum over all your orbitals and the second derivative, but we are not in Hartree-Fock, as will be clear in the following terms. Okay? Then we have said, okay, so this is one part of the energy. We've identified another part of the energy, which is also there in Hartree-Fock, which is simply the classical Coulombic interaction between charges. So that we had written as 1/2 of integral d3r D3 prime M R times M at the given point R prime divided by the distance. Okay? So this is something which appears also in Hartree-Fock, and clearly the energy of many electrons will have a term which looks like this. Another term which we introduced last time was obviously the interaction with the external potential. This is simply an integral over all space, some external potential of R times M of R. And this here, we know this here is what we call the fingerprint of our system, because here this contains all position of the nuclei and the charges of the nuclei. So this here is simply the sum over all nuclei. It is attractive, so it has a minus sign, and is Zi squared divided by the position of the minus squared. Okay? So this is a very easy expression, and we would have guessed it from the beginning. And then we said, well, one thing is missing. We have a kinetic energy, we have a charge repulsion between our charges, like in a classical case. And then all that is missing, we said, we write it as E exchange correlation of N. And this is defined as the difference between what really is the energy of our N electron system and those terms which we can write down. Okay? And we said, well, by comparison with Hartree-Fock, we know it must contain all correlation, because in Hartree-Fock there would be that. And in Hartree-Fock there would be here an exchange term which we do not have, so this is what's called exchange correlation. But we've seen it also contains, in fact, the difference between the real kinetic energy of your many-body system and this term of the kinetic energy. So this, which is called Ts, is also only an approximation to the kinetic energy. And the difference between that term and the real kinetic energy in principle is also. So everything which is not exact is here. So all difficulties. And you might remember when we were talking about Hartree-Fock, I was mentioning the fact that if you have only one electron and you use these equations, then this term here, the Hartree term, seems to introduce an interaction of one electron with itself, because one electron has kind of a probability to be here, to be there. So N of R is defined obviously also for one electron. Okay, you would have only one, but it's the square modulus of the single particle wave function. So if you have one electron, here you would have something as if this electron interacts with itself, which is obviously not there for one electron. The same happens if you have many electrons, but it might be that in some region of space, only one electron is kind of localized and the other electrons are somewhere else. In that case, you would also have in that region of space an interaction of the electron with itself. In Hartree-Fock, this is not a problem, because in Hartree-Fock we write -1/2, the exchange term, and for one electron it's exactly what you add. You remember we have added something and subtracted something, because this here comes from the fact that we have a sum over I and over j, and in principle I equals j is excluded. So if you have only I equals 1, then this term does not exist in principle. So we have added I equals j to this and the exchange term. But now what we are doing in DFT is we are keeping this term, including the I equals j term we have added, but the Hartree term, but the exchange term we are approximating in the ways we have seen last time. And this is the source of an error. And this is one of the nasty errors we have in DFT. And that error is called the self-interaction error. Okay? So if you have the region of space where you have somewhere very localized electrons, which happens, for example, if you have a typical case is, for example, you have transition metal atoms or something where you have d electrons. D electrons are very, very much localized in space. Okay? So the d electrons will have a very strong Hartree interaction with themselves. Okay, because they are all localized in a very narrow area of space. So you have a huge part here. Typically, the approximations you do here for exchange does not compensate this exactly, and you are stuck with huge self-interaction errors. Okay? This is where it comes from. Okay? It comes from the fact that in Hartree-Fock you would not have any of these problems because one term cancels the other. But in DFT you approximate this term, but you keep the exact term here, and therefore this cancellation of errors is not there anymore. So when you read somewhere self-interaction error, and this is really one of the big things disturbing anyone who's working on such materials, then this is where it comes from. Okay? So last time then we said this here obviously must be something very, very complicated because it contains everything which is really difficult is contained in this term. And then I said you like a miracle, there is a very easy approximation to this which works surprisingly well. You remember? So, and the typical or the basis of all approximations of this term here is writing this as an integral over all space, the density at that point times some exchange correlation energy density taken for the value of the density at that point. So this epsilon is not a functional, this is a function of the density at that given point. Okay? So this here is called a local approximation. It is called typically local density approximation. So this seems really too easy to be working in any way, but it works. And the epsilon which one plugs in here is such that if the density was constant everywhere in space, then you get the exact result. So we were talking last time about the homogeneous electron gas, so a gas, so electrons which have the same density everywhere. One can calculate there with some quantum Monte Carlo methods exactly the energy as a function of what this density is. And then by writing down this term, and this term does not exist in homogeneous electron gas because there are no atoms. So by writing down what this term is and this term is, you can, by the difference, obtain this here for the homogeneous electron gas, and this is how one obtains an approximation for this. So this works really, really surprisingly well. And I mentioned last time also that the reason why it works surprisingly well is the fact that this approximation satisfies several exact constraints one knows which this must satisfy. Okay? And because it has these properties, this is at least today's understanding, it works quite well. Okay, so in principle we now have an expression within GFT for our energy. We have an approximation for the kinetic energy, we have these terms, and we have a well-controlled, well-defined approximation for this. Okay? So in principle now we are in game. We have an expression for what we are looking for, the energy of our many-body system. And now the next step we must do is we minimize it. Okay? Questions so far? No? Okay, so let us minimize this. So, to minimize means we calculate the derivative with respect to our variable, and our variable is, well, in principle n, but we have to minimize with respect to these phi's, because n itself is a function of the phi's. Okay? So what we have to minimize is the quantity. So we minimize the quantity, what I call E of phi, minus, and then you have here, we have to minimize in presence of the constraint that these orbitals are orthonormal. So how many constraints do we have? Well, that's the number of pairs of orbitals we have. So sum over I and over j, lambda I j, and the constraint is that phi I, phi j minus delta I j. So this quantity must be minimized. So let's write it down. If we take the derivative with respect to phi complex conjugate k at r. Let's first look what happens if we derive the density with respect to this. So if we calculate delta n of r, say at any position r prime, with respect to phi k complex conjugate at a position r. Well, if you look what the definition is, n at any position depends only on the phi's at the same position. So one thing which comes out is delta r minus r prime. Okay? So one thing is we will n at a different position does not depend on phi at another position. Okay? So r and r prime must be the same. And then if you take here this with respect to k, this means in the sum only the element k survives, I equals k, and you derive with respect to this, so you have simply phi k to the position r. Okay, this is, and we will need this because we want to derive with respect to our basic variables, which are the phi's, but some terms depend only on n. So we will do the chain rule, we will derive with respect to n, and then n with respect to phi. And this will give us a term. So what we obtain is the following. Look at the kinetic energy. Here we have phi I complex conjugate. So the sum will again go away. Only the term I equals k will survive. Okay. We derive with respect to this, and we simply obtain minus h bar square over 2m, the second derivative of phi k. This is the derivative of the kinetic energy. So this is minus h bar squared divided by 2m phi k r. So the derivative, most of our thing is missing. So then in the next term, in the Hartree term, we derive first with respect to n at one position. Let me call it n of r. Okay. So if we derive with respect of n of r, one of the two integrals goes away, one of the integrals survives. Okay. And we have n divided by this here. But we have here n and n, so we have twice this term. Once we derive with respect to this, once with respect to that, but it gives the same thing, so this cancels a factor 1/2. So we will have plus integral over d3 r prime n of r prime divided by r minus r prime. So this is the derivative of the energy with respect to n. Now chain rule, we add this times n with respect to this here, just 1 second. This means, obviously, we are always talking about one position, and we obtain also here times phi k r. Yes?
How do you obtain that delta function?
Which delta function?
Delta r minus r.
Ah, no, this is just to say n of r prime at the position r prime does not depend on the Concham orbitals at a different position. Okay? If you derive the density at this point with respect to phi k at a different point here, I take an r and r prime, then this is 0.
I just
Look at the definition. N at the position r prime depends only on the phi's at the position r prime. Okay? So if you derive n at r prime with respect to the phi star at a different position, you look here to I've written n, then this is 0.
I expected on the psi k.
So?
On the psi k, I expected on the psi k.
Yeah, but so if you write dn of r with respect to phi k of r, then we do simply this.
Oh.
Okay, so here we obtain this. So you all see that these two terms here, they lead to twice the same thing. Here again, this depends on the density, but here it's very easy to derive with respect to the density because this will give you simply the external potential. So here you have plus V external position R. And now also here we have dn with respect to the orbital, which again gives you the orbital by k r. The last term, whatever is the functional approximation we plug in here, we know it depends on n. So we take first the derivative with respect to n at a given point, and then chain rule again. So here we have the E exchange correlation with respect to n at our position r times 5k. So these are the terms which come from the energy. Simply the derivative. Then we have this term here. We have a complex, here no density, but the orbitals. Okay. So the complex conjugate of the orbital appears only here. So we have I equals k, and what is left is minus the sum over j lambda k j, and the derivative is again 5k. And this must be 0 in a minimum. So it looks very much like what we had found already in Hartree-Fock, because you see here you have a single particle operator acting on phi k, another operator acting on phi, another operator acting on phi k, another operator acting on phi k. So this here really looks like a single particle Hamiltonian acting on an orbital is equal to some numbers times the ground. So you obtain, like in Hartree-Fock, we obtain an eigenvalue equation. So minimizing the energy with respect to n leads to an eigenvalue equation. And we have therefore h, the Kohn-Sham Hamiltonian, times the orbital phi k is in principle sum over j lambda k j phi j. And like in the case of Hartree-Fock, the reason that we can use any unitary transformation amongst the orbitals without changing the density or without changing the kinetic energy, therefore we do not change the energy if we take a rotation, which makes this here diagonal. So we can choose this lambda matrix diagonal. Okay. And then this here is simply epsilon k phi. Okay. And what is this H Kohn-Sham? How did I write it? The Kohn-Sham Hamiltonian is kinetic energy plus this here is typically called a Hartree potential, V Hartree of R, plus an external potential this functional derivative here is typically called V exchange correlation of R. And here we are. So it is similar to the equations we had in Hartree-Fock, but not the same. In the Hartree-Fock Hamiltonian had a kinetic energy, had a Hartree term, had an external term, but here we had simply the exchange potential, while here we have the exchange correlation potential. And this here naturally depends on the approximations we do for this term. So in LDA it is one expression and so on. But there is one clear difference. So in DFT, the exchange correlation potential is always a so-called local potential. Local potential means it depends only on R, not on two positions, not on R and R prime. Okay? The reason is E is a functional, it's the number, the exchange correlation energy function, You derive it with respect to the density at one position r, and this defines you the exchange correlation potential at that position. Okay? So whatever the approximation you plug in here, because as long as it depends really only on n, you will always have a derivative with respect to n times the potential, the Kohn-Sham orbital at that point. So this here in DFT is always local. It is always a local potential. It is a local potential, not because we do a local approximation here, but because the exchange correlation term depends by definition only on the density. And in Hartree-Fock here, the exchange term of Hartree-Fock is not a local potential. You remember what it looks like? We exchange in Hartree-Fock was, if you might remember, minus 1/2, and then we have phi of r prime, so the sum of I, phi I of I prime, phi I complex conjugate of r divided by r minus r prime. Okay? So this is something which depends on r and r prime in Hartree-Fock. So in Hartree-Fock you have here a non-local operator, but in DFT you have always a local operator. That is a very, very important distinction between the two approaches. They have in common that one ends up with a Hamiltonian, either the Hartree-Fock Hamiltonian or the Kohn-Sham Hamiltonian, which is a single particle operator. So this here, independently if you have the density function exchange correlation potential or the exchange for Hartree-Fock, it always acts on a single particle orbital, either on the spin orbitals of Hartree-Fock or on the Kohn-Sham orbitals of DFT, but always on a single particle orbital. Okay? So do you understand that there are two different kinds of locality we mean? One kind of locality is that we will approximate most of the times the exchange correlation, which we do not know what it is. We have to approximate it, and the approximations are typically local, or what one calls semi-local. So one writes that this functional is an integral over all space, and then at every point in space you do something locally here. This is why it's called local density, and why this is a local approximation here. But even if that was a very complicated expression, a very non-local expression, very fancy dependence on n at many points at the same time, whatever it is, but as long as this here is simply a functional of n, then what appears in the minimizer here is the derivative of it with respect to the n at a given point. So this is always a quantity which depends only on that one point, not on r and r prime. Okay. Good. So we have another common feature between Kohn-Sham or density function theory and Hartree-Fock. In Hartree-Fock, you remember, you needed to know the solution to write down the equation you solved. Because, for example, the exchange part depended on the phi's, but the phi's you obtained by solving the equation. You remember that? This was called self-consistency. And here we have exactly the same problem. Because we have a Hartree term. For writing down the Hartree term, we must know what the density is. We have an exchange correlation term which depends on the density. For knowing what this term here is, we need to know the density. Okay. So we need to know the density to write our Kohn-Sham Hamiltonian. And only once we know the Kohn-Sham Hamiltonian, we can solve it in order to obtain phi's, and from the phi's, the density. Okay. So it's exactly the same issue, that we need to know the solution in order to write down the equation from which we get the solution. Okay? So it's the same thing in principle. In Hartree-Fock, what we had is, we had to guess what the orbitals are, and then we could write the Hamiltonian. In DFT, we have to guess what the density is. So it is nearly the same, but it's not exactly the same problem, DFT and Hartree-Fock. Okay? In one case, you guess what orbitals are. In the other case, you guess what the density is. But again, you have to start with the guess, and then you update the guess. So this is what I want to write down next. We know that the Contram Hamiltonian depends on the density and of R. And it does so because the Hartree term and the exchange correlation term depend on the density. So therefore, we need the so-called self-consistent solution. And this is done similarly to Hartree-Fock, but I write it up because it is a little bit different nevertheless. So what one starts with is, again, with the guess. You guess what n, a starting density n0 might be. Again, very often one chooses for the guess of the initial density simply random numbers, a random function everywhere in space. Okay? But obviously the density is also the guessed density, which is random, is such that its integral over all space gives you the number of electrons, and then it's never negative. So it has the right physical behavior, but it is just some number, some function which can be anything. Sometimes people take the density as that of isolated atoms, so you know where the atoms are. You put each neutral atom has a given density, and as a guess one might start from atomic densities, or one starts from random numbers. It is assumed. Yes?
In the previous lecture, you told us that this exchange correlation contains also corrections to the kinetic energy.
To the?
Also corrections to the kinetic energy.
Yes, exactly.
Yes.
In principle, it contains also the difference between what we write as kinetic energy and what the real many-body kinetic energy would be.
But finally, you're saying that it leads to the local. We have the local potential.
No, it doesn't lead to. We make a local approximation.
A local approximation, but it was.
This is this one here. What you mean is independently of the approximation that it leads to a local potential. Yes, this is simply because when you try to minimize the whole expression, you have to calculate this derivative of this with respect to n. Okay, and if you have a functional of n, so whatever it describes, also kinetic energy describes whatever it needs to be there. All the differences between the exact energy and the other terms we have. So, but we know, because of the mathematically proven Hohenberg and Kohn theorem, that this is a functional of n. Okay? We do not know its shape, but we know this is a function of n. So if you derive this with respect to n at a given point, you obtain a quantity which we call the exchange correlation potential, which depends on that position at which you have taken the derivative. So it's really the derivative of this here, as long as you write this really only in terms of the density, is something local.
But at least we know some of the things it contains. For example, the equations to the kinetic energy. Can we talk of a local kinetic energy?
Obviously, yes. It does not contain the... Yes, it does. Because, I mean, in principle, even if we do not write all the other terms, we know from Hohenberg and Kohn that the energy of our system can be written, we do not know how exactly, but it is a functional of n. If you derive this functional in order to minimize it, you will always have to calculate the delta E with respect to delta N at a given position. Okay? This is what you have to write and then to equal to 0. Okay? So you have this term here. And this here is always something which is some expression, some V at a given position R. Because it cannot depend on another position. So yes, one can write in some way, so this here is, the energy is not local, but you end up, when you minimize it, with an expression which is locally on R, even though it contains, for example, the kinetic energy. But this does not mean the energy, you see, the function itself is very highly non-local, for sure, the exact function. It's what is local is, in order to minimize it, the term which appears in the equation to minimize this. In our case, in the Kohn-Sham Hamiltonian here, the exchange correlation term. That is a local term. Okay, so we said we start from a guess. Then we set our label, our counter L to 0. Then we build our density N. So from this density here, we build our Kohn-Sham Hamiltonian at the level N from our density N at the level N. Okay, so once we know the density, we can write our Hamiltonian. Because once we know what, or we guess what the density is, we have an expression for it, we can write down this term, that term. So we have our Kohn-Sham Hamiltonian. So we build a Kohn-Sham Hamiltonian from that density at the iteration N we have. Having this thing here, we solve our Kohn-Sham equations. H Kohn-Sham times phi is epsilon times phi. And these phi's I call phi out. Okay. So we have an operator. We calculate its lowest n eigenvectors and eigenvalues. And these n eigenvectors, we call them the eigenvectors out. From those, we build the density as norm squared of these orbitals. So we obtain a new density because we now have orbitals. Then we check is an out similar enough to what we used, so the NL. If it is the case, we have finished. Then we have N is our N out, and we calculate E dft with this density. But typically, the density which comes out is not the density which comes in. So if this is not the case, like in the Hartley 4 case, we have to mix. And we set N for the iteration L plus 1 is alpha times N out plus 1 minus alpha times N at the previous iteration. And then you set L becomes L plus 1 and you do the next iteration. So if you compare with the SEF cycle, self-consistent field cycle, which I had written down in the Hartree-Fock case, it is nearly the same thing. Only in Hartree-Fock you guess what the orbitals are, and then you build the Hartree-Fock Hamiltonian from those orbitals. You also solve a single particle equation. You compare your result with the previous one. If not, you mix something and so on. Only that in DFT all works on the density, while in Hartree-Fock you have to work either with the so-called density matrix or the orbitals. So whenever you use, I don't know, Quantum Espresso or VAS, Forecasted, or any of the codes which do DFT for you, what you will find is in the output, it first says, okay, I'm calculating this and that system, it repeats you what it's doing, and then it says iteration 1, and then it is calculating, it's solving this. Then it says, okay, self-estimated accuracy is, and then it's probably a large number, so it has to continue, and then it says iteration 2, iteration 3, iteration 4, and the accuracy is always becoming better, and hopefully it's becoming better and better by every iteration. And after a certain number of iterations, this check will be true, and then the code can print you out the energy. All this, obviously, given some approximation to exchange correlation, which might be LDA in the easiest case. Good. So since the two things are so similar, and people always or easily get mixed up, I would like at this point to make kind of a table to compare what density function theory is and Hartree-Fock. So, so let's make this table. So on one hand we write properties of Hartree-Fock. And here we write what DFT. So the most important difference is in Hartree-Fock we are trying to approximate the many-body wave function. And we approximate by saying it is a single determinant, but we approximate the many-body wave function. In DFT, there is no notion of a wave function. We have the Kohn-Sham orbitals, but we do not plug them into the determinant, and we do not claim that they are an approximation to this. Because we have here a consistent approximation to the real wave function, here we have a variational principle. Which says that the Hartree-Fock energy is always larger than the exact. So we've always an upper bound to the energy. In principle, it could even be equal to larger. But in fact, this is never. While the energies we get out of DFT, they are not controlled because we do not make an approximation on the wave function. We have no variational principle, and without a variational principle, we cannot say that our energy is always larger or always lower than the exact one. So this is not variable. So in Hartree-Fock we have no functional. Okay, we have directly an expression for the energy. While in DFT we have the exchange correlation functional. And that needs approximations. The biggest difference between the Hartree-Fock Hamiltonian and the DFT Hamiltonian is that in Hartree-Fock you have a non-local exchange potential and here we have only local potentials. I mean, I hope it is clear what it means. So, a non-local potential is such that you have integral dr prime, and then you have v of r and r prime times the orbital at r prime, and this here is non-local. While here you have no integral, and you have directly v of r times phi of r. Hartree-Fock has the advantage that it has no self-interaction error. Here we have SIP, self-interaction error. And the self-interaction error again comes from the fact that we approximate exchange, but we leave the Hartree term, and therefore there is no exact cancelling. In Hartree-Fock, you do not get any correlation by definition. So you have always uncorrelated energies, and this is the main reason why people are not using Hartree-Fock by itself, because the correlation energy is typically important. And here you have an approximation to correlation. So also in systems where correlation effects are important, often DFT with the approximation and the functions we have can work. Yes?
Can you please repeat how the self-interaction error comes about?
Yes. So for this you have to look at Hartree-Fock. So Hartree-Fock energy. You remember where it comes from, the Hartree-Fock energy. It comes from saying we have a single determinant and we calculate the diagonal matrix element of the exact Hamiltonian with the single determinant. Okay? Each of these determinants has these n phi i's, okay, which are then in a given order and so on, like always in a determinant. So if you calculate this, then you end up with the term for kinetic energy, which comes from the kinetic, and so on. And the two-body term, which is here, which is the 1 over R1 minus R2. So the two-body term in this Hamiltonian, it leads to two terms. One term looks like 1/2 integral phi I complex conjugate at R phi I of R phi j at R prime phi j at R prime divided by R minus R prime. And you have here, the most important thing, a sum over I and j must be different. Why must they be different? Because each element appears once in the determinant. Okay, so you cannot have that that the two are the same. Okay. So this is one part which appears, and then I can already see if these two sums would be independent. This is what leads to n of r. This leads to n of r prime. Okay, and this in the end gives you the Hartree term. And then the other term which appears, in fact, if in the two determinant we have the different permutations for the first two terms, we got the minus 1/2. Again, also here the double integral over dr and dr prime, sum over I different from j. And here we had phi I at r, phi j complex conjugate at r, and phi j at r prime, phi I complex conjugate at r prime, divided by r minus r prime. So we have this term here. In both terms, the I equals j is excluded. This is what one obtains if one calculates this here as we have done. Okay. Then we have said, well, we would really like to write here the density, but to write here the density and here the density, we need the term, we need these two sums to be independent. We need here a sum over all i's and here a sum over all j's. So we have added here the term I equals j. Okay. This leads to the Hartree term, which appears in Hartree-Fock and in DFT. But we have made the mistake of I equals j. In Hartree-Fock, this is not a problem, because we simply, here you see is a different sign. We had also here the I equals j term, and then this here, if I equals j, these are exactly the same. So in Hartree-Fock, we've done no mistake by doing this, and all is exact. But now in DFT, we keep this term here, which includes the I equals j term, but this term here we approximate it in our functional. And the functional typically does not cancel this I equals j term we have added here. And this is where the self-interaction error comes from. So, and because you are working on transition metals, I mean, the fact that one needs the plus, the Hubbard U term, variable DFT plus U, which cancels precisely self-interaction error, this is precisely related to this. So if one adds in the DFT, so for you who do not work with this yet, but so one can add some corrections to DFT, to the functionals, and one adds something which looks like a Hubbard U, and that is precisely something which tries to cancel out the self-interaction error in an approximate way. So this is a big issue. So here we have no self-interaction error because we keep both terms. Here we have introduced this unfortunate error. From a practical point of view, since here we have to evaluate the exchange terms, and these are on a computer very slow because you have this double sum, which is inevitable here, while here you can do one sum independently from the other. So in a computer, when you have many electrons, so these sums might be large, this here is very fast, this is very slow to calculate typically. So since in DFT you do not calculate this, typically a DFT calculation is much, much faster than a Hartree-Fock calculation. Okay? So from a practical point of view, Hartree-Fock is you need to evaluate exchange, and that is typically slow. In DFT, normally is no need for Hartree-Fock exchange, and therefore this is faster. Because this local approximation for exchange correlation, they are really super fast. They are never the computational bottleneck. They are the most complicated thing to get right, but if evaluating once you have an approximation is very fast. Okay. So the reason why, in fact, when people do materials calculation, there's a huge, much larger community in doing this. Is on one hand, it is kind of faster if one doesn't need Hartree-Fock exchange, and on the other hand, the fact that here you never have correlation effects, while you can tune your functions here to get those parts of the correlation which is often important. This is why many people are using this. Hartree-Fock alone by itself is nearly never used. So if you do materials calculation, many people, there's this whole quantum chemistry community which I told you, who do Hartree Fock. But normally if someone does Hartree Fock, one never stops there, but one uses then the Hartree Fock result to add some pieces of correlation. As I've shown you, there was this configuration interaction, singles, correction, doubles, or one does coupled cluster, or one does... There are many things which computational chemists have invented to add pieces of correlation, and this is always done. But the first step in any wave function theory is always first Hartree Fock. And then all the corrections and more complicated stuff is on top of Hartree Fock. Okay? So normally, if someone does Hartree Fock, it is the first step of going further, while DFT is, you do have a DFT result, it is good or bad as a function, if your function is good enough, but one stops there. Okay. Just another thing which is also not a feature of the equations of the approaches, but which you should keep, which you can keep in mind is, both of them have these Hamiltonians. So either the Kohn-Sham Hamiltonian or the Hartree Fock Hamiltonian. Remember, these are single particle Hamiltonians acting on, so not the many bodied ones. But for both of them, one calculates eigenvalues. Okay? And then we say we fill the first several levels, and the others are empty. Especially in the Kohn-Sham world, but also in Hartree Fock, the meaning of these energy levels in principle is not that they are supposed to represent excitation energies or something. Remember, because they come simply from, I have written it even today, from Lagrange multipliers to keep your orbitals orthonormal. This is where they come from. But often people interpret these energies nevertheless as the spectrum of your system. So one calculates the density of states, at which energy do you have states, and so on. So this is something which formally has no justification in the theory, but people look at it nevertheless. How are these eigenvalues distributed? And as a rule of thumb, in Hartree Fock, you always find gaps which are way too large. In Kohn-Sham approaches, you always find gaps which are too small. So the systems always appear too metallic in density functional theory because the gaps are small. This is just an empirical found fact. This is not that one can prove it also. While in Hartree Fock, the gap is always sometimes 3-4 electron volts too large. Okay? Which is not a problem because none of these theories has been built to reproduce spectral properties. Okay? But I mean, since you have these Hamiltonians, you can look at what the eigenvalues are, and one finds, okay, empirically, in Hartree Fock it's always too large, in DFT always too small. So far, you agree or you follow what I said? So Hartree Fock and DFT, they are in a sense very similar, but there are these key things which are different. Okay? And keep them in mind in which sense they are different. Okay? Yes?
The problem of the it's only for materials that have d orbitals, right?
No,
for materials that have p-ES thing?
You mean the gap problem? One cannot say, it depends on the functional. Okay? So there are functionals where systematically, even in DFT, the gaps are too large. What you mean is typically in the normal LDA or GGAs, yes, it is really a d electron problem, but also the other. Even if you calculate silicon, it is too small of the band gap. And silicon doesn't have d electrons. Okay, so I suggest that at this point we do some Socrative. Except if you have some questions.
I'm still on the self-reduction energy. Apart from the mathematical point of view, what is the reality? Is it maybe an electronegative?
So it is the fact, no, it is the fact. So what you have kept is a repulsive term, because it's the Coulomb repulsion. Okay? So what it is, if you have electrons very localized somewhere, for example, d electrons, they will want to spread out because this is a repulsive energy which you're not cancelling correctly. Okay? So the electrons do not like to be confined to one place and they try to spread out. Okay? And this is a problem. Leads to many, many physical problems. And then one adds, in fact, as I said, terms which look like Hubbard U, which you've probably seen in other courses. So Hubbard U's is something which then make sure that the D levels are either completely filled or not completely filled. But so since you have added a repulsive term on something very localized, it means the electrons will have wrongly the tendency not to fill these states correctly. Okay, so I have to switch on this display on. PC, let's hope that it works today. Okay, it works. Good news. Quiz to stop previous correlation. So I remind you that it's ICTP-ES is the classroom we go to. Okay. One, two, three, four. There. Oh, someone new here. Okay, can you please finish and then discuss? Okay, I think we can start to discuss this thing. So, question number 1. Correlation energy, and then the different possibilities are, is the difference between the kinetic energy and the Hartree energy, or is the difference between the Hartree-Fock energy and the exact energy? What is it? Which difference is it? It's B, obviously, the difference between Hartree-Fock and exact. This is really what it is by definition. Is it always positive or negative? Negative. Always negative, okay. Then the other thing is obviously wrong, that it's not the negative of the exchange energy. And F is very clearly wrong, since correlation is really the difference between Hartree-Fock. By definition, there is no correlation in the Hartree-Fock energy. So F is also wrong. Okay. Let me go back to this view which I prefer. Okay, so then question number 2, everyone has right. Correlation energy exists only in many body systems, obviously, because if you have just one electron, then you calculate H psi is E psi, and you have the energy number. So it's really a many body effect correlation. Then we have said that by convenience this makes a distinction between strong and weak correlation. So now strong correlation, A is also called weak correlation, A is also called dynamical correlation. No, because strong, we have strong and weak, and dynamical and static. And dynamical is the same as weak, and static is the strong correlation. Okay, so A is wrong. Then we said the strong correlation effect is if the Hartree-Fock determinant is not the main determinant in your determinant expansion of the exact wave function, but that there are several which are kind of nearly degenerate in their importance. Okay, so then you have strongly correlated systems. So B is right, saying that the strong correlation originates from near degenerates of different determinants. Then very important, van der Waals interaction. Is this a strongly correlated effect or weakly correlated effect? So van der Waals is purely correlation effect. So far we agree. In Hartree-Fock there is no van der Waals interaction. But is this strong correlation or weak correlation? It is weak correlation. And there one sees also very clearly why it's called dynamical correlation. Because remember, what van der Waals comes from is that you have some fluctuation of the density at one point in space. This introduces a dipole field, 1 over R3, to some other point. There it correlates with fluctuations at that point, okay? And then 1 over R3, 1 over 3, we have 1 over R6. So, but it is originated in fluctuations which lead to a dipole in your system. And these fluctuations, this is typically a dynamical effect. So it's a weak and a dynamical effect. So van der Waals is a prototype of dynamical correlation. Then it leads to the Hartree-Fock energy being too low. No. So because in Hartree-Fock energy is always the upper bound, okay, and there is no strong correlation. So if you want, it leads to the fact that the energy is much lower than the Hartree-Fock energy. And then strong correlation can be easily captured by adding single, double, and higher oscillations to the Hartree-Fock determinant. Who said this, in fact? one person said it. This is not the case. So this is a typical way of capturing weak or dynamical correlation is by adding single, double, triple excitations on top of the main determinant, which is Hartree-Fock. Instead, if you have strong correlations, then you really need a determinant which typically is very different. It's not just by some objects only. Okay. Question number 4, 70% of it, right? Is by adding determinants with higher energy, one can lower the energy of a many-body state. This sounds strange, but this is exactly what it is. So it sounds strange to say, I have one determinant, I have the Hartree-Fock energy. Now by adding more determinants, obviously the energy goes down because we have a better approximation to our wave function. However, the Hartree-Fock determinant is precisely constructed in such a way that the Hartree-Fock matrix element, the matrix element of the energy between the Hart and that determinant is the lowest possible one. Okay? We've optimized everything such that the Hartree-Fock determinant is the best single determinant we can have. So if you imagine that you have your exact many-body Hamiltonian. Okay? You write this as a matrix and between different determinants. Okay? So if you have, this might be Hartree-Fock, HE phi determinant Hartree-Fock. This here is obviously by definition the Hartree-Fock energy. If you take any other determinant, let me call it phi, say 1, and one other determinant, phi 1, this here will either be larger or perhaps equal, but cannot be lower than the Hartree-Fock energy. No? Because this here has precisely been optimized to be the best one. Okay? So other determinants have, if you want, a higher energy in this sense. But if you think about HE, the Hamiltonian written in matrix form, you would have here the diagonal element Hartree-Fock. Then here you would have, if I call this E, the energy of determinant 1, and then if you have the second one, E of determinant 2. So these here are all higher, or perhaps equal, but not lower than Hartree-Fock. So you add determinants with higher energy. But since there are then off-diagonal matrix elements, which I have V1, and this I might call V2, V2, and V3, V3. So these are the off-diagonal elements. This would, for example, be phi 1, H, E, phi Hartree-Fock. This might be one of those here. So you have off-diagonal elements, and if you calculate the eigenvalues of a matrix, then the lowest eigenvalue can be, or is generally, lower than the lowest diagonal element. So this is how adding determinants with higher energy lowers your energy expectation value. So you understand what I'm doing? I'm writing my exact Hamiltonian in a basis of determinants. The diagonal element, the one with the Hartree-Fock, is the Hartree-Fock energy. Other determinants must have higher energy. But they are off-diagonal elements of this kind. And now you can very easily test it out. If you have a matrix which is E1, E2 with some off-diagonal element, and you calculate of this here the eigenvalues, you find that the lowest, whatever V is, the lowest eigenvalue is lower than the lower diagonal element. This is how adding determinants with higher energy to your wave function can lower the energy expectation value. It sounds counterintuitive that you add to your determinant, to your wave function, more determinants with which each one has higher energy, but the expectation value can be lower. Okay?
We say already Hartree-Fock is exact, correct?
No, Hartree-Fock is not exact. No, Hartree-Fock is an approximation, obviously. Hartree-Fock would be exact if one single determinant would be the exact many-body wave function. Hartree-Fock is by no means exact. Okay. Hartree-Fock means we approximate our many-body wave function with a single determinant. That is a very strong approximation. And this determinant is chosen such that the diagonal element between a single determinant is lowest. And this is why we have, this here will be the lowest diagonal element. All other determinants will have higher expectation values. But the eigenvalue of your many-body Hamiltonian will go down. Okay, so I remind you that today is Friday. On Monday we don't have class because there is the colloquium or something like this. And we meet on Wednesday. Okay. So on Wednesday we will talk a little bit more about the role of spin in Hartree-Fock and EFT. spin and magnetism, and then we will talk about pseudopotentials. Okay? So, see you next week.